turning. The center of gravity is off the center, and in the middle you got an axle with some bearings inside the axle. So what you see here as a letter T is the force that's on the axle, which is pointing downwards, which is T. So this rotation of the wheel creates a force on the axle, which is a center at the center, which is a downward force T. Now, throughout its rotation, that force remains downwards on this axle. So, where did this force come from? That came from due to the rotation of the wheel, and therefore that circular motion, and there will be a net inward force towards the center. There'll be a centripetal force in towards the center due to the angular velocity, of course, but at the same time something to do with the weight being off center as well. So mg has to come off that capital G there. So what I'm going to do is I'm going to look at the first position at t equals 0 at that position there, and I am going to redraw out the downward force on the axle there. Now that's the same force that the weight is pulled up with, so it's an action reaction. Okay, so there is a inward force on the due to the centripetal force, but there is an equal and opposite reaction at the top. Often in centripetal force, we don't consider the force at the point of rotation, i.e. the center, but there's an action reaction. So at G, there's an equal and opposite force to T pulling upwards. Now, if this is a circular path in this kind of way, then we can write an expression down which is T minus mg equals mv squared over r, and because you have T on the vertical axis in all of these graphs, that will be T equals mg plus mv squared over r. So it's mg, as mg is in the middle here at the beginning at T equals 0, the overall force is going to be above mv squared over r. So this inward force at G that's causing this wheel to make that rotation, centripetal force, is the weight plus this inward force, which is your net force mv squared over r, and that tension there is equal to the weight plus this centripetal force upwards, and due to the action reaction on the axle, then that is equal to that, the downwards thrust they call it. So the only graph that has at t equals 0 the thrust greater than mg is D, so therefore straight away it's D. But if you look at the opposite position, i.e. 180 degrees spin, you'll see that if the thrust still points downwards, which it does, as it's mentioned earlier on in the question here, it's a downward force over one revolution. So the downward force on the axle is still, well, it's still pointing downwards. Then that means, due to Newton's third, the action reaction on the C of G position is opposite to that. So T is, there's a force equal to that in the opposite direction at the C of G position. So therefore, in this position, you get mg minus T equals mv squared over r. The dominant force is always pointed towards the center of the rotation. So therefore here we got mg equals, sorry, not mg equals, T equals if we rearrange that, that will be equal to mg minus mv squared over r. So the force at the top is the weight minus some value, i.e. at that particular position, so below the 180 degrees is below mg, the same amount as it was above mg on the other side, and that expression there is minus mv squared plus mv squared over r over there minus mv squared over r here, and no other graph does that. Graph A looks like it's potentially dissimilar, but at t equals 0, the force is greater than mg.